It's the most powerful technology of our time. But how does artificial intelligence actually work? We're pulling back the curtain. This is AI Deconstructed.
In our last session, we explored the very core of classical symbolic AI, knowledge representation. We discussed how pioneers tried to build minds by handcrafting knowledge. They built intricate systems of formal logic, semantic nets that mapped out concepts like a canary is a bird and a bird has wings, and rule-based expert systems that tried to capture the decision-making of a doctor or a geologist in a massive collection of IFTHEN statements. These systems were brilliant. They were our first serious attempt to bottle human expertise, but this approach, this good old-fashioned AI, had a fundamental problem. It had a ceiling, a very low, very hard ceiling. In the 1970s, at Stanford University, researchers embarked on a quest that felt like it was pulled from the pages of science fiction. They wanted to build an electronic oracle, a digital doctor that could diagnose complex infectious diseases, a ghost in the machine that held the sum of human medical knowledge. They called it Mycin. The ambition was breathtaking. The goal was to create a machine that could think like a human expert, to codify the subtle art of medical diagnosis into pure, cold logic. They painstakingly interviewed top doctors, extracting hundreds of rules. Rules like, if the infection is primary bacteremia, and the patient's site of infection is the gastrointestinal tract, and the site of the culture is one of the sterile sites, then there is evidence that the organism is Bacteroides. Rule after rule, they built a vast knowledge base, a cathedral of logic designed to reason its way to a diagnosis. On paper, it was a stunning success. In controlled evaluations, Mycin's diagnostic accuracy was found to be as good as, and sometimes better than, the human specialists it was modeled on. It was the poster child for a new wave of technology called expert systems, and it seemed to promise a future where digital experts would guide our hands in every complex field imaginable. But here's the mystery. Mycin was never actually used in a real hospital. The project, for all its technical brilliance, was a practical failure. Why? What was the fatal flaw in this early handcrafted approach to artificial intelligence that prevented it from making the leap from the lab to the real world? That question is the key to understanding the single most important revolution in the history of AI. It marks the dividing line between the old world and the new. Today, we will journey back to the age of these expert systems to understand their promise and their ultimate peril. We'll dissect the fundamental limitations that led to a collapse in AI research, an era known as the AI winter. Then, we will explore the revolutionary idea that thawed that winter, the radical notion that instead of meticulously programming a computer with rules, we could give it the ability to learn the rules for itself. Finally, we'll break down the three fundamental ways machines learn today: as a student with a teacher, as an explorer in an unknown land, and as an adventurer learning through trial and error. This is the story of how AI learned to learn. To understand the revolution, one must first understand the old regime. The dominant approach to AI from the 1950s all the way to the 1980s is now often called symbolic AI, or more colloquially, good old-fashioned AI, GOFAI. The central belief of GOFAI was that human intelligence, in all its glory, could be distilled into symbols and logical rules. The crowning achievement of this philosophy was the expert system. An expert system is, at its heart, an attempt to build a perfect digital clone of a human expert's mind for a single specific task. It consists of two primary components. First, there is the knowledge base. This is a massive structured library of facts and, crucially, IFTHEN rules that are painstakingly extracted from a human expert. Think of it as the textbook and the expert's lifetime of notes. The second component is the inference engine. This is the logical processor, the reasoning mechanism that takes a new problem, consults the knowledge base, and chains rules together to arrive at a conclusion. The analogy of a chess grandmaster is useful here. Imagine interviewing the world's greatest player for months. One would write down every strategy, every opening move, every rule of thumb, every heuristic they use to evaluate the board. If the opponent moves their knight to the edge of the board, then their control of the center is weakened. If you have a passed pawn, then you should push it forward. After codifying thousands of such rules, one would program a machine to follow these instructions with perfect, lightning-fast precision. That is the essence of an expert system. The goal was to capture not just the public, textbook knowledge of a field, but the private, little-discussed rules of good judgment, the rules of plausible reasoning and good guessing that truly characterize expert-level decision-making. And for a time, it seemed to work brilliantly. While they struggled with broad, toy problems in very narrow and well-structured domains, expert systems showed incredible promise. Digital Equipment Corporation, DEC, developed a system called XCON in the 1980s to configure complex computer system orders for its customers. It was a task with a dizzying number of components and rules, and XCON handled it flawlessly, saving the company an estimated $25 million per year. In another stunning example, a program called SID was fed the design rules for a new computer chip, the VAX 9000. The program generated a logic synthesis that, surprisingly, exceeded the capabilities of the human experts who wrote the rules, producing a more efficient design. This was the promise of GOFAI made real, a machine that could not only replicate human expertise, but in some cases surpass it. Despite these successes, a deep and fundamental problem lurked just beneath the surface. The systems were described by researchers as being incredibly brittle. This meant that while they performed with superhuman ability within the precise boundaries of their programming, they would fail completely and catastrophically the moment they encountered a situation, however minor, that their creators had not explicitly anticipated. An expert system for diagnosing car engine problems might have 1,000 rules about carburetors and spark plugs, but if it's presented with a car that has a slightly different, newer fuel injection system it wasn't programmed for, it doesn't just perform poorly, it stops. It has no ability to generalize, to reason by analogy, or to handle ambiguity. It only knows what it has been explicitly told. These systems exhibited fragile behavior at the boundaries of their knowledge because, for them, the boundary was an absolute cliff. This brittleness was a symptom of a deeper architectural issue. The GOFAI approach was predicated on the assumption that the world could be neatly and exhaustively defined by a set of human comprehensible rules. But the real world is messy, dynamic, and infinitely complex. The number of possible situations, edge cases, and exceptions is effectively infinite. For any truly complex problem, the search space of possibilities expands exponentially with each new variable. A system that requires a pre-programmed rule for every eventuality is doomed from the start. It's not just that writing all the rules is hard, it's that it is philosophically and practically impossible. The brittleness wasn't a bug to be fixed. It was the inevitable consequence of a flawed premise about the nature of intelligence itself. This led directly to the second major crack in the code, the problem of scalability. As the complexity of a problem domain increased, the number of rules required to model it would explode exponentially. Maintaining this ever-growing web of logic became a nightmare. Adding a single new rule could create unforeseen contradictions with hundreds of existing rules. To manage this, developers had to create fiendishly complex, truth maintenance systems that could track all the dependencies in the knowledge base, revoking old conclusions when new facts were introduced. The manual creation and maintenance of these rule bases became completely impractical for large, dynamic problems, trapping expert systems in narrow, static domains. The technical challenges of brittleness and scalability were immense, but the true killer of the expert systems dream was something far more human. It was a problem that came to be known as the knowledge acquisition bottleneck. This refers to the profound difficulty, cost, and time required to extract knowledge from a human expert and translate it into the rigid, formal language of IFTHEN rules that a computer could understand. The reason this bottleneck exists is explained by a concept from the philosopher Michael Polanyi, now known as Polanyi's paradox. We know more than we can tell. A vast portion of human expertise is not explicit, rule-based knowledge. It is tacit knowledge, the intuition, the gut feelings, the subtle pattern recognition that comes from years of experience. It's the 90% of the iceberg of knowledge that lies hidden beneath the surface of conscious thought. Consider an expert factory manager who can walk onto the floor during a crisis, listen to the hum of the machinery, and instantly know which valve needs adjusting. When asked how they knew, they might say, "I don't know, it just sounded wrong." They can't articulate the precise acoustic frequencies or the complex interplay of vibrations that their brain processed. They just knew. Similarly, a seasoned doctor's gut feeling about a patient is not a simple checklist. It's a subconscious synthesis of thousands of past cases, subtle cues in the patient's expression, and a lifetime of experience that is impossible to fully put into words. This is the knowledge that expert systems needed to capture, and it proved to be the wall they could not climb. The process of trying to do so, called knowledge engineering, was arduous and often doomed to fail. It was plagued by several challenges. There were fundamental communication gaps between domain experts, who thought in terms of their nuanced field, and knowledge engineers, who thought in terms of formal logic. The experts themselves were, by definition, highly skilled, busy, and expensive professionals, whose time was difficult to secure for the prolonged periods of interrogation required. In some cases, the process was even met with active resistance. Experts, quite reasonably, feared they were being asked to program their own obsolescence. One researcher recounted how experts would sabotage projects by pretending to be unavailable, unwilling to hand over the keys to the kingdom to a machine that might one day replace them. The knowledge acquisition bottleneck was the single greatest hurdle that drowned most expert system projects before they ever got off the ground. The confluence of these issues, the overblown hype, the immense cost and inflexibility of the systems, their inherent brittleness, and the seemingly insurmountable knowledge acquisition bottleneck, led to a devastating collapse in the AI industry. By the late 1980s and into the early 1990s, funding dried up, research labs were shuttered, and the very term expert system began to vanish from the IT lexicon. This period of disillusionment and retreat became known as the Second AI Winter. The legacy of expert systems is not one of total failure. Some argue they were victims of their own success. Concepts like rule engines were absorbed into the mainstream of corporate IT and became standard, if less glamorous, tools. But the grand dream of GOFAI, the vision of creating standalone machines with artificial general intelligence through symbolic logic, was put on ice. It became clear that a fundamentally new approach was needed. The field had hit a wall. To move forward, AI would have to abandon the quest to perfectly codify the mind of the expert and instead figure out how a machine could develop expertise on its own. It needed to learn. The thaw that ended the AI winter came from a complete and total rethinking of the problem. It was a paradigm shift so profound that it changed the very definition of what it meant to build an intelligent system. The contrast between the old way and the new way is stark. The expert system approach was a top-down, logic-driven process. First, you interview human experts. Second, you painstakingly encode their knowledge into explicit IFTHEN rules. Third, you run the system and hope the rules covered every eventuality. And when they inevitably didn't, you go back to the experts and repeat the cycle. The new approach, which came to be called machine learning, flipped this entire process on its head. It was a bottom-up, data-driven process. First, you gather vast amounts of data related to the problem. Second, you clean and prepare that data. Third, you feed the data to a general-purpose learning algorithm. Fourth, you allow the algorithm to find the patterns and relationships within the data on its own. And finally, you evaluate its performance and repeat the cycle. This was a monumental change, moving away from the world of symbolic logic and into the realm of statistics and pattern recognition. The central idea was revolutionary. Instead of teaching a computer how to solve a problem by giving it the rules, we would show it thousands of examples of the problem being solved correctly and let it infer the rules for itself. We stopped trying to program intelligence and started trying to cultivate it. This is the essence of learning from data, of learning from experience. But what does it actually mean for a machine to learn? The term was first coined in 1959, decades before it became a buzzword, by an IBM researcher and AI pioneer named Arthur Samuel. Samuel was building a program to play checkers. Instead of trying to program it with the perfect strategy, he designed it to play against itself thousands of times and learn from its mistakes. His program eventually became so good it could consistently beat its own creator. Samuel defined this new field as the field of study that gives computers the ability to learn without being explicitly programmed. This definition perfectly captures this radical departure from hand-coded instructions. Decades later, in 1997, computer scientist Tom Mitchell provided a more formal, rigorous definition that has become the standard in the field. It breaks down the concept of learning into three essential components. A computer program is said to learn from experience E with respect to some task T and some performance measure P if its performance on T as measured by P improves with experience E. Let's break that down with a simple human analogy. First, the task or T is what we want to accomplish. Let's say it's throwing a crumpled piece of paper into a wastebasket. Next, the experience, or E, is the data we gather from trying the task. It's the memory of every single throw, the angle of release, the force applied, the arc of the paper, and critically, the outcome, did it go in or miss? Finally, the performance measure, or P, is how we grade our success. It could be the percentage of successful shots out of the last 10 attempts. According to Mitchell's definition, one has truly learned when the performance measure P gets better as one accumulates more experience, E, as one makes more throws and adjusts the technique based on past outcomes. The success rate improves. This is precisely what a machine learning model does, just at a scale and speed that is impossible for humans. This brings us to a critical clarification, a common misconception that we must clear up right now if we're to build real literacy. People use the terms artificial intelligence and machine learning interchangeably. This is incorrect, and it muddies the water. Think of it like this. Artificial intelligence, or AI, is the broad, overarching goal. It's the entire field of study, the grand human quest to build machines that can perceive, reason, and act intelligently. It's like the entire academic discipline of biology. Classical AI, the rule-based, logic-driven systems we've discussed, was one approach to achieving that goal. It's a major subfield of AI, like ecology, is a major subfield of biology. Machine learning, or ML, is a different approach to achieving the same goal of AI. It's another major subfield. It's like genetics. Both ecology and genetics are subfields of biology. But they are very different ways of studying life. In the same way, classical AI and machine learning are both subfields of AI, but they are very different ways of building intelligence. And later, when we get to deep learning, we'll learn that it is a subfield of machine learning. It's a specific type of machine learning, much like CRISPR gene editing is a specific technique within the field of genetics. So, AI is the goal. Machine learning is a method, and deep learning is a specific technique within that method. Today, machine learning has become the dominant method for building AI, so dominant that it's easy to see why people confuse the two. But as students of this field, we must keep this hierarchy clear in our minds. This process of learning is not a magical, one-step event. A common misconception that paints AI as an unknowable black box. In reality, building a machine learning model is a highly structured, multi-stage engineering discipline. It's less like conjuring a spirit and more like running a sophisticated factory or assembly line for producing intelligence. And in this modern factory, the single most critical and often most challenging raw material is data. The entire process can be broken down into three major phases. The first is the foundational phase, and it is almost always the most time-consuming and resource-intensive part of any machine learning project. The principle is simple: garbage in, garbage out. No matter how sophisticated the algorithm, a model trained on poor-quality data will produce poor-quality results. It begins with problem definition and data gathering. It starts with a clear business question: what precisely are we trying to predict? Do we want to predict customer churn, identify fraudulent transactions, or forecast sales? Once the goal is defined, the hunt for data begins. This data can be scraped from websites, pulled from corporate databases, accessed via APIs, or collected through user activity. This is where a new kind of bottleneck emerges: the data acquisition bottleneck, the challenge of simply getting enough relevant, high-quality data to work with. Next comes data cleaning and pre-processing. Real-world data is notoriously messy. It's full of errors, missing values, inconsistent formatting, and outliers. This step is the unglamorous but absolutely essential janitorial work of machine learning, where data scientists meticulously clean, format, and transform the raw data into a usable state. A crucial part of this stage is data labeling. This applies specifically to supervised learning, the most common type, which we'll discuss in a moment. If we are teaching the model by example, we need to provide it with an answer key. This means manually labeling each piece of data with the correct outcome. For an email spam filter, this means having humans label thousands of emails as spam or not spam. For an autonomous vehicle, it means having teams of people draw boxes around every car, pedestrian, and traffic sign in millions of video frames. This is the modern incarnation of the knowledge acquisition bottleneck. The challenge of getting human expertise into a machine-readable format didn't disappear with expert systems. It simply shifted. Instead of extracting deep, complex rules from a few expensive experts, we now extract millions of simple, shallow judgments from armies of data annotators. It's still a manual, time-consuming, and expensive process, now often called the data labeling bottleneck. Finally, the prepared data is carefully split into three distinct sets. This is a critical step to ensure an honest and unbiased evaluation of the model's performance. The training set is the largest portion, typically 70 to 80% of the data. This is the textbook the algorithm will learn from. The validation set, which is around 10 to 15%, acts as a series of practice quizzes. The data scientist uses this set to tune the model and compare different approaches during the development process. And the test set, the final 10 to 15%, is the final exam. This data is kept in a locked vault, completely untouched during the entire training and tuning process. It is used only once, at the very end, to get a true measure of how well the model will generalize to new, unseen data in the real world. With the raw materials prepared, the process moves to the main assembly line, where the model itself is built and refined. It begins with model selection. There is a vast toolbox of machine learning algorithms, from simple linear models to complex deep neural networks. The choice depends on the nature of the problem, e.g., is it a classification or a regression task, the size and type of data, and whether the model's decisions need to be easily interpretable by humans. A common best practice is to start with a simple baseline model and gradually increase complexity only if necessary. Next is the core step, model training. This is where the learning actually happens. The chosen algorithm is fed the training data through a mathematical process, often involving the minimization of a loss function, which measures the error between the model's predictions and the true labels. The algorithm iteratively adjusts its internal parameters to find the patterns in the data. After an initial training run, the model is put through model evaluation. Its predictive power is tested against the validation set, that practice quiz. The data scientist uses specific statistical metrics, like accuracy, precision, or recall, to score its performance. Based on this evaluation, the process enters a loop of hyperparameter tuning. Hyperparameters are the model's external settings that the data scientist controls, like the complexity of a decision tree or the learning rate of a neural network. The scientist will tweak these settings, retrain the model, and reevaluate it against the validation set, searching for the combination that yields the best performance. Once the tuning is complete and the best performing model has been selected, it faces its final testing. The model is unleashed on the sacred, held-out test set. This single final score is its report card, representing the most honest estimate of its real-world capabilities. A model sitting on a data scientist's laptop is useless. The final phase is about putting it to work. Model deployment, or serving, involves packaging the trained model and integrating it into a production environment. This could be a web server that provides real-time predictions, a mobile app, or an internal business analytics tool. But the work doesn't end there. Monitoring and maintenance is a critical, ongoing process. The real world is not static. Customer behavior changes, new types of fraud emerge, and the data the model sees in production can slowly shift away from the data it was trained on. This phenomenon, known as model drift, can cause a model's performance to degrade over time. Continuous monitoring of the model's live performance is essential to detect this decay. When performance drops below a certain threshold, it triggers an alert that it's time to go back to the beginning of the workflow, collect new data, and retrain or rebuild the model entirely. This reveals a crucial truth about modern AI. The machine learning workflow is not a straight line from data to deployment. It is a continuous, iterative cycle. An ML model is not a static piece of software that is built once and then forgotten. It is a dynamic system that must be constantly fed, maintained, evaluated, and updated to remain effective. This has enormous implications for the infrastructure, resources, and long-term commitment required to successfully implement AI in the real world. Now that we understand the factory that builds these learning machines, we can look at the three primary blueprints it uses. While there are many specific algorithms, nearly all of them fall into one of three fundamental learning paradigms: supervised learning, unsupervised learning, and reinforcement learning. Using a few simple analogies can help make these core concepts clear. First is supervised learning. This is the most common and well-understood type of machine learning. The name itself is a perfect description. The algorithm learns under the direct supervision of a teacher. In this case, the teacher is the labeled dataset we provided. A dataset where every input example is paired with the correct output answer. It's like a student studying for a test with a complete set of practice questions and the corresponding answer key. The goal is for the algorithm to learn the general mapping, the underlying relationship between the questions and the answers, so that it can eventually provide the correct answer for a new question it has never seen before. A great analogy for this is cooking with a recipe. Imagine you have a massive cookbook, which is your labeled training data. Each page is an example. The list of ingredients represents the input features, and the beautiful photo of the finished dish is the label or correct output. By studying thousands of these ingredient-to-dish pairs, you start to learn the patterns. You learn that flour, eggs, and sugar often result in a cake. You learn that tomatoes, basil, and pasta lead to an Italian dish. The ultimate goal is to become such an intuitive chef that when a friend gives you a new, random assortment of ingredients, you can accurately predict what kind of dish you can make, even without a specific recipe in front of you. The real-world applications of supervised learning are everywhere. For example, spam filtering is a classic classification task. A model is trained on millions of emails that have been manually labeled by humans as spam or not spam. It learns to associate certain words, phrases, or sender characteristics with the spam label. Another example is image classification. When a photo app recognizes a face or identifies a picture as containing a cat or a dog, it's using a model trained on a vast library of images that were previously labeled with those tags. We also see it in medical diagnosis. A model can be trained on thousands of medical images, like X-rays or MRI scans, that have been labeled by expert radiologists as either cancerous or benign. The system learns the subtle visual patterns associated with each diagnosis, acting as an aid to human doctors. And finally, there's predicting house prices. This is an example of a regression task, a subtype of supervised learning where the output is a continuous number, not a category. By training on historical data of house features, like square footage, number of bedrooms, and location, and their final sale prices, a model can learn to predict a reasonable sale price for a new house coming onto the market. The second paradigm is unsupervised learning, and it's fundamentally different. Here, there is no teacher and no answer key. The algorithm is given a dataset with no labels and is tasked with finding the hidden structure, patterns, or groupings within the data all on its own. It is a process of exploration and discovery. The analogy here is organizing a massive, chaotic bookstore. Imagine you are dropped into a warehouse filled with tens of thousands of books, all scattered randomly on the floor. There are no signs, no genre labels, no Dewey Decimal System. Your task is to bring order to this chaos. You start by walking around and picking up books. You can't read them all, but you notice patterns. Some books have dragons and wizards on the cover. Others have pictures of food. Still others feature detectives in trench coats. Without any pre-existing labels, you begin to physically group similar books together. You create a fantasy section, a cookbook section, and a mystery section. You have discovered the inherent structure of the data without being told what to look for. This is the essence of unsupervised learning. This approach is incredibly powerful for tasks where we don't know the right labels ahead of time, or where we want to discover new, unexpected categories. For instance, in customer segmentation, an e-commerce giant like Amazon or a streaming service like Netflix uses your purchase or viewing history to group you with millions of other users who have similar tastes. These groups or clusters were not predefined, they were discovered by the algorithm. This allows for highly targeted marketing and personalized recommendations. It's also used for anomaly detection. A bank's fraud detection system works by first using unsupervised learning to understand what normal transaction patterns look like for millions of customers. It learns the typical clusters of spending behavior. When a new transaction occurs that falls far outside any of these normal clusters, for example, a large purchase made in a different country at 3 a.m., it gets flagged as an anomaly, a potential case of fraud, and it's used for topic modeling. News aggregators use unsupervised learning to scan thousands of articles from different sources and automatically group them into stories about the same event. The system doesn't know what politics or sports are, but it can identify that articles containing words like election, Senate, and vote belong together. The final paradigm, reinforcement learning, is perhaps the most ambitious. It's not about learning from a static dataset, but about learning how to make optimal decisions in a dynamic environment through a process of trial and error. The setup involves an agent, the model that can take actions within an environment. After each action, the agent receives a reward or a penalty from the environment. The agent's sole objective is to learn a strategy or policy that maximizes its total cumulative reward over time. A fitting analogy is training a dog or playing a video game. When you're teaching a puppy to sit, you don't give it a textbook on dog behavior. You create an interactive learning loop. When the puppy performs the correct action, sit, it receives a positive reward, a treat. When it performs an incorrect action, like chewing the furniture, it receives a penalty, a stern no. Through thousands of these interactions, the puppy's brain learns the policy. The action sit leads to rewards, while the action chew leads to penalties. It learns by doing. Similarly, an AI agent learning to play a video game explores the digital world by pressing buttons. It gets positive rewards for collecting coins and reaching the finish line, and negative rewards for falling into pits. Over millions of attempts, it learns the sequence of actions that leads to the highest possible score. Reinforcement learning is computationally very intensive and can be slow to train, but it is capable of solving incredibly complex, sequential decision-making problems that are intractable for the other methods. Its most famous successes are in game playing. DeepMind's AlphaGo did not learn to master the game of Go by studying human games, a supervised approach. It learned by playing millions of games against itself, gradually discovering strategies far more complex and creative than any human had ever conceived. It's also used in robotics. It's used to train a robot arm to pick up a novel object. The robot might try thousands of slightly different grasping motions. It only receives a reward signal when its sensors detect a successful lift. Through this trial and error process, it learns a robust policy for manipulation. In autonomous vehicles, while many parts of a self-driving car rely on supervised learning, like object recognition, the high-level decision-making policy, when to change lanes, when to accelerate, when to brake, can be optimized through reinforcement learning. The agent is rewarded for making safe, efficient progress towards its destination and penalized for collisions or traffic violations. And it's used for dynamic resource management. RL is used to optimize complex systems like data center cooling, where an agent learns to adjust thousands of variables to minimize energy consumption while maintaining safe temperatures, or to manage an electrical grid by learning the best policy for storing and releasing power from renewable sources based on supply and demand. To summarize these three distinct approaches, supervised learning is like a student with an answer key, focused on prediction. Unsupervised learning is an explorer, charting unknown territory and looking for hidden structure. And reinforcement learning is an adventurer, learning to master a skill through trial, error, and feedback. These three pillars, supervised, unsupervised, and reinforcement learning, are the roadmap for our next 3 episodes. We will dedicate an entire session to each one, starting with the most common, supervised learning, in Episode 8. Then we'll explore unsupervised in Episode 9 and reinforcement in Episode 10. Our journey today has taken us from the ambitious, logic-filled halls of 1980s AI research to the data-drenched, statistics-powered factories of the modern era. We witnessed the rise and fall of the expert system, a brilliant but flawed attempt to handcraft intelligence one rule at a time. We saw how its brittleness, and most importantly, the knowledge acquisition bottleneck, revealed a fundamental truth: that much of what makes an expert is unspoken, intuitive, and impossible to codify. The failure of that first wave of AI plunged the field into a winter of disillusionment. The thaw came from a paradigm shift, a complete change in the central question of the field. Instead of asking an expert, "What are the rules?" researchers began asking a machine, "Can you find the rules in this data?" This shift from logic to learning, from rules to patterns, is the single most important development in the history of artificial intelligence. It unlocked the ability to tackle the fuzzy, ambiguous, and complex problems, like recognizing speech, classifying images, and understanding natural language, that had been utterly impossible for the rigid, symbolic systems of the past. As we've seen, this new paradigm is not magic. The machine learning workflow is a rigorous, iterative, and data-hungry engineering discipline. It is a powerful statistical engine, not an infallible oracle. It has its own bottlenecks and its own profound challenges. But understanding this shift is the key to understanding the AI revolution we are all living through today. It is the foundational concept upon which nearly every modern AI application is built, from the camera in your smartphone and the recommendation engine that suggests your next movie, to the most advanced tools being used at the frontiers of scientific discovery. The story of AI is the story of its long, difficult, and ultimately successful journey to learn how to learn. We have successfully navigated the great pivot. We've closed the book on the age of good old-fashioned AI and opened the first chapter on the age of learning. We've seen why the old way of handcrafted rules was a dead end, and we've built the entire framework for the new way, the data-driven workflow and the 3 great pillars of learning. Our foundation for the rest of this course is now set. Next time, we build on that foundation. We take our first step into the most common and powerful paradigm of all, supervised learning. We will move from what learning is to how it is precisely mathematically achieved.
You've been listening to AI Deconstructed. Join us next time as we unpack another layer of the technology shaping our future. Until then, stay curious. Subscribe for more.